Hello friends, welcome to the first lecture of Engineering Thermodynamics, Advanced Thermodynamics course. This course has two important roles to play in the learnings of Masters and PhD students at Thermal Engineering stream, in the Thermal Engineering stream. One is, of course, it tries to or helps you to brush up whatever you learned at your undergraduate level and maybe at the school level about thermodynamics. The second it does is to remove several misconceptions and wrong understandings, which is a very important role that it plays, because quite often at undergraduate level and school level, either the people who taught you themselves understood thermodynamics to a limited extent and therefore introduced misconceptions into your understanding. Even when that is not the case, language has a limited ability to communicate things. So whatever the faculty members told you, you understood it in your own way and therefore understood it probably correctly, probably wrongly. So there are misconceptions that get introduced into the understanding of thermodynamics. So this course would strive to, number one, revise the basics that you learned at your undergraduate level, and number two, also try to remove misconceptions that if there are any. So there is a very pertinent quote about thermodynamics. Let me remove my face from the screen and share the screen of PowerPoint presentation that I have, which will be quite revealing for you. So we'll be talking about a quote by Arnold Sommerfeld, one of the exponents in thermodynamics, about thermodynamics. What he said is thermodynamics is a funny subject. The first time you go through it, you do not understand it at all. The second time you go through it, you think you understood it, except for one or two points. This is basically what many of you people told me in the previous class when we discussed about it. The third time you go through it, you know you do not understand it, but by this time you're so used to the subject that it doesn't bother you anymore. Right? So that is the level that I would intend to take you to at the end of this course. Just kidding. Let's try to see how much we understand. And Otto Redlich is another author of thermodynamics who wrote a book on thermodynamics in 1950s and 60s. So he says thermodynamics, like the Helen of Troy, has always been admired much and much reviled. Reviled is basically criticized and spoken against by people. So we all grudgingly admire thermodynamics, don't we? So that's basically what this statement says. Well, fine. This is people's opinion about thermodynamics. Let's get on to business. One thing that we need to understand about thermodynamics is that it was not discovered or invented in the way that we study in textbooks. It has a history to it. And thermodynamics is actually the science of how things work and how things cannot work. And therefore, things that work or did not work came first, and the science came later, like in many other places where technology precedes science. Particularly with respect to energy, people, as the civilization of mankind improved, man realized very soon that his own muscle power is quite limited. Sorry about the gender thing here. When I say his and mankind, I'm actually talking about all genders. We are not just talking about male gender here. I'm sorry about that limitation. It's again a limitation of the language. I don't have gender neutral way of putting this. So mankind, when the civilization advanced, very soon realized that the desires of mankind cannot necessarily be fulfilled by the muscle energy of the man alone or the human being alone. So very early in science, people started working with water wheels, which are rotated by the flowing water. Then came animal muscle power. So for a long time in history, and even today, human beings use animal muscle power because human muscle power is not as powerful. Horsepower is definitely more than human power. So horses and cattle, oxen were used for doing man's work, mules, various animals. And then came steam. So from the Newcomen engine onwards, steam came to be used as a source of motive power, which humans wanted, and that caused the Industrial Revolution, whose history most of us already understand. So if you try to look at the history of thermodynamics, what came first, of course, is the Newcomen engine and the James Watt engine. And along came Sadi Carnot. Sadi Carnot was the one who first enunciated second law, not exactly in the form in which you study, because the form in which you study it is stated by Kelvin, Planck. So Kelvin and Planck were two different people, or Clausius. But Sadi Carnot was the first one who basically got the understanding of the second law and enunciated it in a particular form. In fact, the history goes quite interesting. His father, Lazare Carnot, was an engineer who could build, water wheels, and therefore harness the power of water that flows from a higher elevation to a lower elevation to produce work. And that was also the time when caloric theory of heat was prevalent. So people thought that heat is a massless fluid and it flows from a higher temperature to a lower temperature, just like fluids or liquids flow from a higher elevation to lower elevation under gravity. So Sadi Carnot, the son of the engineer Lazare Carnot, started thinking, how does James Watt's engine work? Because James Watt's engine was invented just before this period in which he stated these laws. So he started thinking about how steam engines work. So he said, okay, just like water flows from a higher elevation to a lower elevation and makes wheels rotate and does work, caloric flows from a higher temperature to a lower temperature and makes things work. And then he tried to find out, can all caloric be converted into work? And that is what resulted in the second law. So it is a misnomer to call it the second law. It should have been the first law, but it is called the second law because in the logical order in which we study, this comes second. It does not come second as such. We'll come to that a little bit more. The first law came about 50 years later when Joule did his experiment to establish the equivalence of heat and work. So Joule's experiment was trying to do work on an enclosed tank of water by, let's say, a falling weight under the action of gravity, rotating a paddle wheel inside the water, and with whatever accuracy of temperature measurement that was feasible in the 1850s. He measured the rise in temperature of water and was able to show that there is a unique correspondence of the rise in temperature of water with the height of fall of the mass, and therefore he was able to establish an equivalence between heat and work, and there came the Joule's constant J, which is 4.2 joules per calorie. In the International System of Units now today, that J has become 1 because we use joules both for heat as well as work. But then this came about in the 1850s, and then based on that, the first law was understood that energy can be looked upon as heat or work, and the first law was stated or enunciated about 50 years after the second law. The third law came further 50 years later, somewhere in the 1920s and 30s. The third law is about absolute entropy and absolute entropy going to zero at absolute zero in perfect crystals. And when people recognize that the first, second and third laws have been stated, and then they talked about the concept of thermal equilibrium, they said measurement of temperature requires a law which is even more fundamental than the first law. But the first, second and third laws had already come into being. So they said, okay, it has to come before the first law, so let's call it the zeroth law. So that's the way it actually got named. So this actually, every time when I talk about this in the classes, I get reminded of a joke that one of our senior professors, Professor N.K. Tiwari, who retired from Mechanical Engineering Department in the late 90s or maybe early 2000s, he used to state this joke, and that applies beautifully to this. So the joke goes like this, that there was a happily married couple, a man and wife, and as a year rolled on, they had their first baby. So they were quite happy that the baby has arrived, and because he was the only baby, they didn't feel the need to name him. They used to call whatever they felt like at any given point in time. And as time rolled on, another year or two later, a second baby was born. Now, in order to distinguish him from the first one, they called him Chotu. Chotu means a small one, right? Those of you who are not familiar with Hindi. And as it would happen, stories are stories. So another couple of years later, they had a third issue, and now they had a serious problem. Now look, we have to name these two kids. But by this time, the name of Chotu had stuck, because he was called Chotu uniquely. So if you call anybody Chotu, he would respond, not the smaller one. So they had to name him, keep his name as Chotu, and name the other two consistently with him. So what would they name them? So in an interactive class, I would have actually conducted a quiz on this. Because this is a recorded lecture, I'll give you a moment to think about it, and then I'll give the answer myself. Yes, I think some of you got it right. They named the first one as Cho 1 and the third one as Cho 3, so that the second one remains Cho 2. Good, okay. So that's the history of the laws of thermodynamics. So we understand that the heat and work are distinguished actually by the second law. The first law treats them both as the same. So if there is stored energy, that can be changed by heat or by work equally or equivalently. There is no difference between the amount of change that would happen in the energy because of heat or because of work. So first law cannot distinguish between heat and work. The distinction between heat and work actually came from the second law, but is often taught before the first law is taught in terms of heat and work. So there is a patchwork that happens here. So we define energy, heat and work, and then define first law, and then second law comes much later. And we all have accepted this quite nicely, but did not ask questions about why is there two forms of energy when both of them do the same thing. If I add heat, it increases energy. If I add work, it increases energy. If I remove heat, it decreases energy. If I remove work, it decreases energy. So what's the big deal? Why do you have two things? We don't ask that question when we teach the first law to students, nor do the students ask the question because the teachers teach them, so they have to learn, right? So in classical thermodynamics, because the history brought the first law and the second law first and first law second, but then when we wrote the books of textbook, we wrote the heat and work first and then the first law and then the second law, and there is a reverse dependency. One understands that heat and work are distinct only by second law but not by first law. Now this kind of back and forth definitions is not becoming of a mother science such as thermodynamics. So some authors of thermodynamics actually recognized it. Otto Redlich, whose quote I talked about, Helen of Troy, was one of them. And so a more formal and smooth treatment was attempted without this back and forth. So I would follow the textbook by Professor P.L. Dhar, which actually follows Otto Redlich's treatment for the definitions and laws of thermodynamics, and the rest of it we could teach from other textbooks. So the textbook by P.L. Dhar would be used for the initial parts of the course. Now, coming to the definition of thermodynamics, you go through various different books that are written on thermodynamics. All of them have a definition of thermodynamics which has similar elements but slightly different from each other. So we'll put this definition across here. So the word thermo has to do with interactions by contact, interactions between objects or between systems when they are put in contact with each other. What happens is a thermal process, thermo. And dynamic is a process when interactions happen without a contact but through a connection that facilitates the contact, facilitates the interaction. Okay. So we'll explain these things as we go on right now. So thermo is a certain form of interactions which came to be known as heat. The interactions when objects are put in contact with each other. When one object is warmer than the other, there is transfer of heat, so it is heat. So thermo stands for heat or interactions by contact. So we would define them in this way so that heat and work also are understood by the nature by which they are different. Right. Similarly, dynamic is about interactions without contact. But who interacts? Objects or systems interact, so we'll need to define about them, we'll need to talk about them. So thermodynamics is usually defined as the science of transformation of energy from one form to the other and its interaction with matter. Okay. So matter constitutes objects or systems and they interact, and while interacting there is energy transfer, transformation between them, and that is the science that thermodynamics basically tries to describe. Now all of these words need definition: interaction, contact, energy, transformation, all of that. So we will come to that. This course will basically take a macroscopic view only. So it's called the classical thermodynamics. What does it mean? It means that it is in contrast with the microscopic or the molecular level study, which is called the statistical thermodynamics, which bases itself on the kinetic theory of gases and quantum mechanics and describes what happens in reality through interactions of molecules and the ensemble of such molecules. But in this course we will not be looking at that. We will be looking at macroscopically observable systems, objects and quantities, and therefore it's called the classical thermodynamics. It has its own beauty because we all understand that the thermodynamics as we understand it, the classical thermodynamics as we understand it, is capable of describing processes in various systems without needing too much detail to be understood. Right? So that's why we'll be looking at that. Let's start with a couple of basic definitions. Okay. The first thing that we talked about was that the thermodynamics deals with objects and their interaction in the presence or absence of contact. So there are three words there which are in red and underlined: objects, interaction and contact. Let's try to understand these things. Whenever we need to observe any object, right? Suppose I want to observe this box. Then in order to observe this box, I need to at least notionally separate it from the surroundings so that I can observe it. Suppose I want to measure the temperature of this body, then that is a form of observation that I would do. Now, in order to do that, I need to make sure that the temperature of this body is not changing because of its interaction with the neighboring objects or the surroundings. So, at least for the period of my measurement, I need to isolate it. And in real life, we'll never be able to really isolate any object. So, suppose I want to measure the temperature of coffee in a cup. I would just put a thermometer into it and measure without thinking that if I put that thermometer, it is going to absorb some energy, and therefore if the thermometer was initially colder than the coffee, then the coffee would cool down because of the presence of the thermometer. We don't actually think about that. Or if we think about that, we'll need to see whether the amount of energy that is absorbed by the thermocouple or thermometer is significant as compared to the energy that is contained in that, so that by removing that much of energy, are we substantially affecting the measurement. So, in order to clearly understand it, in order to observe any object, we cannot interact with it. We'll need to actually observe it when it is isolated. But when it is isolated, observation is not possible, and therefore the observation needs to be at least notional, in the sense that, number one, when I measure the temperature of the cup of coffee and it is still cooling down because it is interacting with the surroundings, I need to prevent its interaction with the surroundings. So I need to completely insulate it from the surroundings so that at least for the time that I am measuring the temperature, it is not losing heat to the surroundings. Or the rate at which it is losing heat to the surroundings does not change its temperature so rapidly that during the time of my measurement it changes. So the concept of time also is there in my mind. So if I measure temperature of the cup of coffee, which is cooling, let us say 10 degrees Celsius per hour, or if I do it per minute, it is 1/6 degrees Celsius per minute. And when I make the measurement, it takes normally 1 or 2 minutes. So the change in temperature would have been 1/6 to 1/3 degrees. And usually 1/6 or 1/3 degrees is smaller than the least count of the measuring instrument that I am going to use, and therefore it can be neglected. So there are so many things that actually come in the measurement, but strictly speaking, when I want to observe the temperature of that object, I need to actually isolate it and observe it, right? So this isolation is a concept that comes in there. And when I isolate this object, let's say a cup of coffee is completely insulated from the surroundings, then it should be actually having no spontaneous changes happening within itself, in the sense that all points inside the cup of coffee should have the same characteristics. So let's say the same temperature throughout, so that there is no transfer of energy happening from one point to the other, and therefore the change in temperature spontaneously happening inside it. Whenever that is happening, it is still not in equilibrium. For example, if I take a hot lump of steel from an oven and place it in atmosphere, then the inside of it is still probably at the initial temperature, but the surroundings are cooling the top surface. So within that object, there is a change, like a range of temperatures that is there from inside to the surface. So this object is by no means in equilibrium. But if I completely isolate it or insulate it such that the entire block is at the same temperature after some time and it's not undergoing any spontaneous changes, then we call it an equilibrium with itself. Equilibrium of the object with itself is different from the equilibrium of the object with the surrounding objects. That is, if I keep two objects next to each other, one which is different in temperature from the other object, then there is a transfer of energy that happens from one object to the next object. That is the change in the state of equilibrium of one object to the other. But when the two are at the same temperature and I put them together, then there is no further interaction happening and they are in equilibrium with each other. So equilibrium is looked upon in two different ways: equilibrium of an object within itself and equilibrium of two different objects put adjacent to each other when they attain the same properties. Now the equilibrium that we are talking about in this particular case is the equilibrium of one object within itself, right? So now let's try to understand these terms. Object is that part of the world around us which we would like to study, and we identify the object by drawing an imaginary boundary around it, saying that whatever is inside this boundary is the object and whatever is outside it is the surroundings. So that is what we typically define. A collection of objects is also called sometimes a system. The object sometimes is interchangeably used as system in most textbooks. So surroundings is that part of the world in the vicinity of the object. So now surrounding is not the entire rest of the universe other than that, which is quite often it is made out to be. So if I'm observing a cup of coffee, let us say, then the surroundings would be the reasonable neighborhood of that region, which might be able to affect that cup of coffee in the period of observation, or which might be affected by the cup of coffee in the period of observation, or in the reasonably comparable period to the period of observation, but not really the entire universe. So suppose I keep a cup of coffee on my table and measure its temperature. Your home, where you are sitting right now, need not necessarily be part of the surroundings, and therefore the object plus its surroundings constituting the universe. Universe is a much bigger thing. Your home and my home are still finitely a few hundred kilometers apart at most. But then the universe is millions of or billions of kilometers big. So please, let's not use such exponential terms which are often used in many textbooks. So we would say object plus the surroundings constitutes a part of the universe, but it's not the entire universe. Okay, so that's the way we'll understand it. And isolation is basically when no form of interaction is happening between the object and the surroundings. I'll stop the first lecture here. We'll continue this in the next lecture because we had decided to do short lectures. So I'll stop at this point and we'll continue in the next lecture. Okay. So let me bring my face back to facing. So we'll stop here and meet in the next class. Thank you.